Hey guys, today we're taking a look at the graph and properties of the direct variation equation y equals kx squared. Now before we jump into that, recall what our last lesson was about. We looked at the properties and the graph of y equals k times x. That's the direct variation equation, and we said that that was going to be a linear function. It passed through the origin, 0, 0, and had a constant rate of change. Well, we're going to kind of take a look at the differences and the similarities that our graph today of y equals k times x squared produces. So first off, the graph of y equals k times x squared is the graph of a direct variation equation where we are squaring our independent variable. Now, it is a set of all points x, y that forms a parabola. So if you take a look here over at the right, our graph here has this U-shape. This U-shape is known as a parabola. It passes through the origin as well, 0, 0, and it always contains the point 1 over and k up or down. Another term that we're going to learn today is the vertex. The vertex is the minimum or the maximum point of a parabola. So for a direct variation equation, y equals k times x squared, our vertex is going to be the origin 0, 0. So over here on the graph, you can see this is a minimum point. As my parabola comes down, it bounces off of the origin and then goes back up. Now, this creates some symmetry, and this is a reflection symmetric graph. This is the symmetry property of all parabolas. The graph of y equals kx squared is going to be symmetric over the y-axis. And you can see here that this branch here in quadrant 1 is just a reflection of the branch here in quadrant 2. Now, if you don't remember the quadrants of the coordinate plane, I sketched out a little xy axis here for you for quick reference. We start in the top right-hand corner with quadrant 1, then moving over to the top left is quadrant 2, bottom left is quadrant 3, and then quadrant 4 is our lower right. All right, let's take a look at example 1 here. Example 1 says we're going to use Desmos again to create a sketch of y equals kx squared, where k is going to be a slider. So again, this is going to allow us to dynamically see what happens when we change the value of k. Then answer the questions below as you explore. All right, so we have our sketch opened up here, and you can see that this is our parabola where y is equal to k times x squared. Right now, the value of k is 1. So this is really just the graph of y equals 1x squared. You can see that it passes through the origin, and you can also see that it passes through the point 1, 1. Well, as we drag this slider further to the right, where we have positive and larger values of k, you can see that this graph, this parabola, is getting more narrow or skinnier. It's being pulled towards that y-axis. If I go all the way up here to 10, you can see it continues to get skinnier and skinnier. All right, I'm going to widen this now by looking at values between 1 and 0. I'm still staying positive, but you can see here that as I go between 0 and 1, I have a much wider parabola. So it's kind of like a flattening or a fattening of that parabola. So back over to our notes, it just simply asks us to drag that slider back and forth. We're going to drag it to 2, and then we're going to drag it to where k is equal to 4 and sketch both those graphs. So we're going to start off by plotting our vertex point 0, 0. And since k is equal to 2, this is the graph of y equals 2x squared, I know that it's going to pass through the point 1 over and 2 up. All right? And the reflection of that should be negative 1 over and 2 up. Now, 3 points is good enough for me to kind of give a sassy sketch of what that parabola looks like. So here we go. There's our graph of y equals 2x squared. Now, the graph of when k is equal to 4 will give us the graph of y equals 4x squared. Again, this is a direct variation equation, and it's going to pass through the origin, and it's going to contain the points 1 over and 4 up. And negative 1 over and positive 4 up. So again, this is going to kind of pull a little bit closer to that y-axis there, and here is our graph of y equals 4x squared. All right, finish this sentence. As your positive values of k got larger and larger, what happened to the graph of y equals kx squared? And we're going to say here that it got skinnier. How do you spell skinnier? Skinnier, something like that. How about we add to that more narrow? There you go. There's a math teacher's explanation instead of a English teacher's. It's going to be pulled towards the y-axis. All right. Next up, we're going to drag the slider for k now to be -1, -2, -5. We're going to just give a sketch of one of those graphs on this same set of axes over here, and we're going to talk about the effect that that negative value of k has on the graph. So let's go back to our little slider here in Desmos. Here we are in positive values, and now we're between 0 and 1, and here we are when k is equal to 0. Notice that's a horizontal line. And now we're going to go into the negatives. All right, so here's where k is equal to -1. You can see that this parabola now opens down. It's reflected over that x-axis. And as we get larger and larger values of, or negative values of k, you can see again that it's pulling towards that y-axis and getting skinnier and skinnier. But it's just opening down instead of opening up. All right, so again, we're going to graph now. Let's take the value when k was equal to -2. We're going to graph y equals -2x squared. So it's still going to pass through the origin, and now it's going to pass through the points 1 over and -2 down. And then -1 over and -2 down because of that reflection symmetry. And here is our parabola. All right, answering the question, what effect did a negative value for k have on the graph? We are going to say that it reflected it over the x-axis. Oops, let's try to spell that correctly. X-axis. And now our parabola opens down. And when our parabola opens down, it's going to appear in quadrants 3 and 4 instead of in quadrants 1 and 2. So finishing these statements, when k was less than 0, that means it's negative, our parabola opened down. And when k was greater than 0, that means k is positive, our parabola opened up. And over here on the right, I'm just going to make note that this is quadrants 1 and 2 when it opens up, and when it opens down, it's in quadrants 3 and 4. Finally, it says, at what point do all of these functions pass through no matter what k's value? Well, that's our origin, 0, 0, and that's the vertex of our parabola. All right, let's look at a math problem here involving a parabola. It says the braking distance can be modeled by the following function. Distance is equal to 1/20th of your speed squared. Find the following rates of change. Well, remember, rates of change is a fancy way of saying slope. So we're going to find the slope of the line that is described, between the following points, and we're going to describe what this means in the context of braking distance. So over here, we're finding the rate of change between the 2 points, 10, 5, that's this one here, and 20, 20. So yeah, it's this one right here. And if I draw that line between those two, here is the slope, or here is the line whose slope we're trying to find. So following our slope formula, we're going to take 20 minus 5 and divide that by 20 minus 10. Remember that slope is the change in y over the change in x. So these are the difference in my y coordinates divided by the difference in my x coordinates. All right, doing the math on that, we're going to have 15 over 10, and that's going to reduce to 1.5. Now, let's explain what this means in the context of braking distance. Remember, we have our y variable on top, and the units for y is braking distance in feet. And our x variable is in the denominator here, and our units for our x variable is miles per hour. So really, this 1.5 is 1.5 feet per 1 mile per hour. So as you increase 1 mile per hour in your speed, you have to allow for 1.5 more feet of braking distance. Next up, we're going to find the rate of change from the point 2020 now to 50, 125. So here is the point 50, 125. We are now looking at the rate of change, or the slope, between these 2 points. So following the same format here, we're going to take the difference in our y values, 125 minus 20, and divide that by 50 minus 20. All right, that's going to give us 105 over 30. Now, that's going to reduce to 3.5. And again, keep in my units, I have feet per 1 mile per hour. So you can see here that this 3.5 is different than the 1.5. We have increased our rate of change, or our slope, between these 2 points. And that's the truth about parabolas. It does not have a constant rate of change or a constant slope. It actually has an increasing slope as you go further along that parabola. So we say, since the slope, or the rate of change, between two different pairs of points on the graph are not constant, then the graph of d equals 1 over 20 s squared is not a line. Well, we know this. We know it's a parabola. And therefore, a single number does not describe the slope of this function. All right, that's it for today. We'll see you tomorrow in class.